this very nice workshop to Natal. I'm going to talk about SU4 symmetric spin-orbital liquids, and I'm going to start by telling where the SU4 symmetry comes from. This will be Monte insulators with heavy magnetic ions, so strong spin-orbit coupling. So it's somewhat surprising that it gets such a high symmetry from a model system that has strong spin-orbit coupling that usually reduces the spin rotational symmetry from SU2 to some discrete symmetry. But then I'm going to show you that we actually get some spin models for effective magnetic moments with total angular momentum j equals 3/2. And the interesting cases are where these j equals 3/2 moments are on the honeycomb lattice or hyperhoneycomb lattice, or more generally other tri-coordinated lattices. And then I'm going to discuss some candidate spin-orbital liquids for this model on these lattices and discuss their energies calculated by variational Monte Carlo. And this is work done in collaboration with my former student, William Nature from São Carlos, and also with Professor Eric Andrade, also from São Carlos. Okay, thanks to the previous talk, I can say this very briefly. So I'm going to talk about spin liquids in the sense of something like Anderson's resonating valence bond state. So this will be Monte insulators where the spins are strongly interacting, but they don't order even at zero temperature. So the picture is something like a coherent superposition of singlet states that does not break spin rotational symmetry nor lattice symmetries. And in addition, we want spin liquids to have fractional excitations in the sense that if you create, say, a triplet excitation on top of this ground state, this excitation is described by having spins 1/2 that can be at arbitrarily large distances. Then we say that the elementary excitations, the spinons, are deconfined. And of course, we usually associate spin liquids with frustrated magnets, like the Kagome lattice that we heard about in the previous talk. But more closely related to what I want to talk about are the so-called Kitaev spin liquids. So here is the Kitaev model on the honeycomb lattice. It describes spins 1/2 that are localized on the honeycomb lattice, and they interact via this anisotropic interaction that is Ising type. But the coupling between nearest neighbor spins depends on the direction of the bond. So on the honeycomb lattice, we can divide the links into 3 different directions and label them by x, y, or z. And then say if you take a pair of nearest neighbor spins on the x link, they're coupled by this Ising interaction of s, x, x, x. And likewise for the other 3 directions. And here I'm going to use this notation. I'm going to label the direction of the bonds by this index gamma, which is x, y, or z, and write the Hamiltonian for the Kitaev model and other models like this. And here we have a system where there's no geometric frustration because the honeycomb lattice is bipartite, but the kind of spin liquid physics that we get comes from the fact that the frustration is in this dependence of the interaction on the spatial direction of the bond. So it's like the spin doesn't know in which direction it would like to order because it looks to its nearest neighbors, and each one of them prefers ordering in a different direction, x, y, or z. And of course, it's known that the Kitaev model is exactly solvable. It's solved by a representation of spin 1/2 operators in terms of Majorana fermion bilinears. So if you plug this representation with Majorana fermions, which are operators that are Hermitian and the anti-commute into this Hamiltonian, you just get a model where the Majoranas hop freely on the honeycomb lattice in the presence of a static Z2 gauge field. So it's pretty much like a free fermion model with integral and so on. But not long after Kitaev's proposal of this model, for different reasons, for topological quantum computation and so on, it was realized that the Kitaev type interactions are relevant for actual materials like the iridates. So here I'm showing the lattice structure for sodium iridate. This is a layered material where the magnetic ions are iridium 4+, which have this electronic configuration 5d5. The iridium ions sit inside an oxygen octahedron with this geometry, which is edge sharing, and the octahedra form this honeycomb lattice. So the first question here is, what are the local degrees of freedom, or is your effective spin? So if we take into account the crystal field, which is an octahedral crystal field, you split the d orbitals into T2d and Eg levels with 5 electrons for iridium 4+ in the T2d level, so it's a single hole. And you have to take into account that the T2d level has an effective orbital angular momentum of L equals 1. And here we have strong spin-orbit coupling because it's a heavy ion, it's iridium. And so you put spin-orbit coupling on top of that, and you further split the T2d levels into a J equals 3/2 multiplet, which is fully occupied, and a single electron in a J equals 1/2 level. So if in addition you have strong electronic correlations, a large U in the Hubbard model, you can have a Monte insulator where now your system is described by local moments, Monte insulator with J equals 1/2 spins, very similar to S equals 1/2 for 3D materials. However, since this is coming from a strong spin-orbit coupling, the effective spin model is not necessarily a Heisenberg model. It could be something different and anisotropic. And in fact, Kitaev and Jackelli and Kaliulin consider the exchange model, the exchange interactions that you can derive starting from a Hubbard model and looking at the exchange paths for this kind of geometry with edge sharing octahedra. And they showed that if you project the states onto this J equals 1/2 doublet, the interactions that you get are exactly, at least for the ideal case, 90-degree bonds, are exactly what Kitaev had written down for the exactly solvable model. And in the particular case of sodium iridate, it turns out that the complete model is more complicated. It's so-called Kitaev-Heisenberg model. There are perturbations so that this material actually ends up ordering at low temperatures. But recently, there is good experimental evidence for a quantum spin liquid state in this other iridate. So the game we wanted to play here is actually, instead of looking of J equals 1/2 states, we can look at, instead of a D5 configuration, let's look at the case of heavy magnetic ions with a single electron in the D1 orbital, again with octahedral crystal field and strong spin-orbit coupling. And in this case, just go through the same argument, you end up with a single electron in now the J equals 3/2 multiplet that lies lower than J equals 1/2. And in this case here, I'm assuming that we have still the cubic symmetry preserved down to low temperatures. So this degeneracy here remains, so a fourfold degeneracy. For instance, if there is a Ian-Teller distortion of these oxygens, like the tetragonal distortion, this would be split. But the motivation for thinking about the states with cubic symmetry actually came from this material. It's a double perovskite, where there is experimental evidence for no structural transition. The material remains cubic down to very low temperatures, and there we had quite a good number of experimental results that suggested this could be a spin liquid state. So we proposed a quantum spin orbital liquid of some exotic kind with a nodal line spectrum of Majorana fermions, but I won't talk about this. So the story here will be really about J equals 3/2 states and what kind of spin models we get for such systems. And first of all, we need a convenient notation to represent the states in this J equals 3/2 multiplet. So I'm going to use this notation here. Jz runs from -3/2 to +3/2 for the 4 states. But we can represent these 4 states in terms of 2 pseudospins that I'm going to call S and tau. The first one I will call pseudospin, the second one pseudo-orbital. The pseudo here is just to remind you that we had the original spins and original orbitals before we put in the spin-orbit coupling. So these are like the states are already superpositions of eigenstates of orbital and spin angular momentum. So they're more complicated than that. But in any case, the pseudo-orbital here, the name makes sense in the sense that if we look at states with the same tau z, but opposite pseudospin, they're conjugated by time reversal symmetry, and they have the same electronic distribution. So in some sense, it's really connected with orbitals. But then flipping the pseudospin, the SC, corresponds to applying time reversal, so that has some effect on the magnetic moment as well, and that will be relevant later. Okay, so we play the same game as Jacqueline and Kaliuli. Start with a multi-orbital Hubbard model on this kind of geometry with edge-sharing octahedra. So we have a on-site repulsion U, also Hund's coupling JH, and then we look at the the spin interactions that we generate to second order in hopping. And the model is terribly ugly. I won't bother with the details. I'll just point out that these actually, all the terms in this Hamiltonian can be written in terms of those two pseudospin operators, pseudospin and pseudo-orbitals. The interactions involve not only s dot s or tau dot tau kind of terms, but also multiples of the j equals 3 halves operators. With j equals 3 halves, you can have up to quadrupoles and octupole moments. They all show up here. And here are the exchange coupling constants written in terms of Tu and the Hund's coupling. But notice one thing, that if we set the Hund's coupling JH to 0, all these j's become the same. So I can throw away all these terms except the one on the first line. So there is a huge simplification in this model in the limit of 0 Hund's coupling. And it becomes like this with some redefined j. It's still not very obviously symmetric. There is some dependence here on the interaction of the bond, just like in Kitaev's model. And the interaction is involves not only the pseudospins, but also the pseudo-orbital operators. However, we can simplify it further if you apply a trick that is known in the literature on the Kitaev-Heisenberg model. You can do these 4 sublattice pi rotations, where you divide the lattice into 4 sublattices and you rotate by pi, either on the x, y, or z axis, depending on the sublattice. We do that for the pseudospin operators. And for the pseudo-orbital operators, we also do a pi rotation, but just with 2 sublattices. So this lattice has to be pi-partite. And if we do this, use this trick, you can transform the Hamiltonian to this form, which is now a lot simpler, and it's explicitly SU2 cross SU2 symmetric. But maybe you're familiar with this form. This is the Hamiltonian, which actually has an enhanced SU4 symmetry. It can be written like this, where you have this lambda-lambda coupling, where lambdas are all the 15 generators of the SU4 group. So we have 15 operators. The total, the sum of all the operators on all the sides commute with the Hamiltonian. And I should emphasize that these are the operators in the rotated basis, right? After we do these 4 sublattice pi rotations, sometimes called client transformations, I should say. And this is interesting because now we have a model that has SU4 symmetry, and it's known that having SUN symmetry with large n enhances quantum fluctuations and favor quantum disorder states as opposed to classical states like Néel states. And the question is if n equals 4 is large enough to have a spin liquid. And indeed, SU4 models have been studied on many different lattices. If I go back, you can see that it looks like a Kugel-Konski model, where you have this Heisenberg interaction, if you like, where the interaction depends on the state of the orbitals as well. And this type of Kugel-Konski model with this enhanced SU4 symmetry has been studied just as a simple starting point for more realistic models in different materials. The interesting point is that it has also been studied on the honeycomb lattice, and there it was studied with not only variational Monte Carlo, but IPAPs, these projected entangled pair states. And there is very good evidence that the ground state is not magnetically ordered, but is some sort of pi-flux quantum spin-orbital liquid, where you have the deconfined excitations are complex fermions at quarter filling. Quarter here because there are 4 different colors of these fermions. And this state is such that at quarter filling, there is a Dirac point in the spectrum. So this would be a gapless spin orbital liquid. In this paper here by Yamada, Oshikawa, and Jacquelli, which appeared before ours actually, they proposed an experimental realization of this model in the zirconium, on the honeycomb lattice in zirconium trichloride, which is somewhat related to ruthenium trichloride, another Kitaev material that has already been realized and studied a lot. And in this case, we just replaced D5 by D1 with zirconium. But as far as I know, there are no experiments in it yet. It would be interesting to see if there are actually evidence for this emergent SU4 symmetry in this material. So, like I said, there was already evidence that on the honeycomb lattice you get this pi-flux gapless spin liquid. We decided to look at other lattices where you can play the same tricks. And there's a number of three-dimensional lattices with coordination number equals to 3, where you can put the same kind of interaction. And we chose the hyperhoneycomb lattice, which is sort of looks like it's one of the three-dimensional extensions of the honeycomb lattice, in the sense that you can think that you twist some of the bonds out of the plane, and now instead of having hexagons in the loops, the smallest loop actually has 10 sites. The motivation for taking this particular case was that the Kitaev model is exactly solvable on this lattice. You just put the same kind of interactions with, there's also coordination number 3. And in that case, you also get a gapless spin liquid, but with nodal lines in 3 dimensions. So it's a different kind of a topological state. And also, there is experimental realization of a Kitaev Heisenberg material on this hyperhoneycomb lattice, that is lithium iridate, beta lithium iridate. However, it's order. Again, the Heisenberg interactions are strong enough that you are not in the Kitaev spin liquid phase. But perhaps we could think about having some D1 material with the same kind of lattice structure that could realize this SU4 symmetric model on the hyperhoneycomb lattice. And then the question is, what kind of ground state to get on this lattice? And to address this question, I'm going to work out some mean field theory for the spin liquid. So we can represent the generators of SU4 in this way. So here we have the 4 colors, M and M label 1 through 4. And we can represent these generators of SU4 in terms of fermion bilinears. These are complex fermions now. And we can generate a ground state variational wave function by looking at the mean field Hamiltonian, where these fermions hop on this hyperhoneycomb lattice with some mean field parameters chi-ij, like hopping parameters, which we fix for different specific NZs. And then you can generate a variation of state by taking this mean field ground state and projecting onto the physical Hilbert space by imposing single occupancy, 1 fermion per site. And here is the first state that we looked at. This is the zero-flux state, so it's the simplest case. So we just take those mean field parameters chi to be uniform on this hyperhoneycomb lattice. And here we're using this representation of the composition of the hyperhoneycomb lattice as a base-centered cubic lattice with an 8-site basis. So these are the 8 sites represented here, and this line just represented the hopping is the same. And what are the sites that are connected by this hopping or by the bonds? And in addition, you have to impose this quarter filling condition on average. So there will be 1 fermion per site to represent this local spin. And in this case, we can calculate the band structure that comes out of this mean field Hamiltonian, and the Fermi level is here fixed by the quarter filling condition, and it crosses the bands here. So this defines a state that has a Fermi surface in 3 dimensions. So this would be a spin on Fermi surface state, the zero-flux state. Another state we looked at was the pi-flux state. Is also relatively simple. It's time reversal symmetric. And in this case, we have to modify the mean field parameters, changing the sign of these hoppings on the dashed line here that connect the sites in the unit cell. And in this case, it's interesting that instead of a Fermi surface, we get band touching at Dirac points here. Here's the Fermi level. And these are anisotropic Dirac points in the sense that the dispersion depends on the direction that you move in the Brillouin zone. So along some directions, the dispersion is linear, and in the other directions, it's quadratic. So I personally was hoping that this state would have lower energy after projection, but that turned out not to be the case. Eric did the variation of Monte Carlo for this size of the lattice, and here are the results. There is very little finite size dependence, and the lowest energy corresponds to the zero-flux state of complex fermions. We also looked at the representations with Majorana fermions, but they have higher energy. So the zero-flux state wins, and then we decide to check if it would be stable against perturbations. One perturbation that is important when you talk about SU4 systems, SU4 symmetric systems, is tetramerization, because it's the analogous of dimerization for SU4, because now you can form local singlets between 4 sites with this fundamental representation of SU4, and then we check that the zero-flux state was stable, because the energy only goes up if we allow the spin liquid to tetramerize. We also looked at competing order states, and here we put back the Hund's coupling, because it lifts the degeneracy of the classical states, and we can analyze the stability of the order states using the so-called linear flavor wave theory. This is just a linear spin wave theory using a Holstein-Primakov representation of SU4. And we found that out of the states that we considered, which were 2-color or 4-color states, only the stripe state that is represented here by this figure. This would be the direction of the magnetic moments after we undo the force of lattice rotation. Only this state is stable, but still it has higher energy than the spin orbital liquid state, the zero-flux state. So we haven't actually found any transition from this proposed spin liquid states to ordered states, even when you turn on Hund's coupling. So the question is, if the system has some order state somewhere, what kind of state it is? That's pretty much an open question. It's probably some non-collinear order that we haven't considered. And let me just advertise briefly something I did with Vanildo Carvalho and Herman Freire, who are in the audience. So I started talking about the Kitaev model. And you can ask, is there an exactly solvable model that looks like this J equals 3 halves models that I was talking about with pseudospin and orbital degrees of freedom? And in fact, there is. It was proposed by Hongyao and Donghai Li. This model is exactly solvable, again, by a Majorana fermion representation of this spin and orbital operators. However, it does not come out naturally from this kind of J equals 3 halves systems that I was talking about. So there is no concrete realization of such Hamiltonian. It would be nice to have one, because once you have SU2 symmetry, like in this model, and you know for sure that the ground state is a spin liquid, you can talk about spin transport. So for instance, in the original paper, they show that if you perturb this spin liquid with some 3-spin interaction, some chiral interaction that breaks time reversal symmetry, you open up a gap, and the phase that you get is a chiral spin liquid that has a quantized spin Hall conductance. And then recently we looked at signatures of the surface states, Majorana edge states, in spin transport through the interface with a normal metal, if we can have such a spin liquid. So with that, I will conclude. So the main message is that there are a lot of interesting new spin models when you consider Monte insulators with strong spin-orbit coupling. In general, these will be bone-dependent exchange reactions. So I talked about the case of J equals 3 halves moments on the honeycomb and hyperhoneycomb lattice, and argue that the model has this emergent SU4 symmetry in the case of zero Hund's coupling, and I should emphasize that it's an SU4 symmetry in the rotated pseudospin basis, so there's a question of how this could be observed. And we looked at some variational states for the spin orbital model on the hyperhoneycomb lattice, and from what we can tell, the lowest energy one is a quantum spin orbit liquid with a spin on Fermi surface. So thank you.